In this mini course, we discuss how to apply Knowles' and Magar's adult learning principles and Bloom's taxonomy for college new hire training in semiconductor equipment manufacturing.
We will discuss Knowles' adult learning principles, Magar's principles of learning, Bloom's taxonomy, practical strategies. We will also cover how to connect theory to real work for role-specific applications and discuss best practices for effective training of adults. Introduction and overview. Semiconductor equipment manufacturing is a highly specialized technical field that requires robust training programs, especially for adult learners entering the industry from college. Unlike traditional classroom learning, adult education must cater to learners who are autonomous, experienced, and results-driven. A framework-based approach, drawing from adult learning theory like Knowles' andragogy and Bloom's taxonomy, ensures that these new employees gain not only theoretical understanding, but also job-ready competencies. College graduates in science and engineering need content that acknowledges their foundational knowledge, yet bridges it to real fab environments and tasks. Effective training must deliver practical value, connecting complex semiconductor equipment theory to hands-on work, such as tool operation, yield improvement, and safety practices. The key challenge is creating training that both respects adult learning preferences and equips individuals with the ability to perform technical roles confidently and safely. This module introduces a blueprint for accomplishing just that, using proven learning principles to guide content design. Knowles' andragogy. 6 principles. Malcolm Knowles' 6 principles of andragogy are foundational for designing impactful adult learning. First is the need to know. Adults want to understand why something matters before committing effort. In the fab, explaining how learning a tool calibration procedure improves wafer yield immediately builds buy-in. Second is self-concept. Adults prefer self-directed learning. Empowering new hires to navigate modules at their own pace reinforces responsibility and engagement. Third, adult learners bring valuable experience from prior education or work. This knowledge must be welcomed, discussed, and connected to new content. Fourth is readiness. Adults learn best when content relates directly to their immediate roles, such as chamber cleaning or troubleshooting alarms. Fifth, orientation to learning emphasizes solving real-world problems, which makes fab case studies and performance data ideal training tools. Lastly, motivation is intrinsic, driven by growth, responsibility, and professional pride. Recognizing these principles accelerates training and shortens the path to fab floor readiness. Bringing Knowles' principles to semiconductor training. Implementing Knowles' principles in semiconductor training begins by focusing on real fab problems. Rather than presenting abstract theory, courses should highlight current challenges, like reducing defect density or improving preventive maintenance routines. Next, training should be collaborative. Adults learn better when actively engaged in problem-solving with peers. This means replacing passive lectures with simulations, peer discussions, and small group troubleshooting tasks. Trainers must also clearly explain relevance. For example, showing how process drift affects yield ties, training content directly to key performance metrics. Involving learners as partners respects their autonomy. Engineers and technicians should be invited to share feedback, shape content focus, and reflect on their learning journey. Prior experience should be mined, inviting learners to draw connections between past projects or university lab work and current fab tasks. A great example is using deposition training to show immediate impact on wafer yield, reinforcing the power of practical, adult-centered instruction. Magar's Principles of Adult Learning. Magar's 6 principles provide a practical playbook for hands-on adult education. First, ready to learn means content should match each learner's job role and career phase. A technician new to LPCVD should receive entry-level simulator exposure, not advanced recipe design. Second, learners must set goals. Training should allow them to co-create objectives, such as earning tool certification within 30 days. Third, Active participation is critical. Adults learn better when they engage through simulations, shift handovers, and peer instruction. Fourth is reinforcement. Spaced repetition using daily quizzes or supervisor review sessions boosts retention and confidence. Fifth, meaningful content matters. Trainees need to see how mastering a dry clean protocol reduces contamination and tool downtime. Finally, learners must practice skills. Simulation environments, mock troubleshooting sessions, and in-tool shadowing offer structured, real-world practice. Consider the technician who uses a simulator, daily feedback, and goal tracking to get certified on LPCVD tools within 4 weeks, a clear model of Magar in action. Bloom's Taxonomy Framework. Bloom's taxonomy organizes learning from basic recall to complex creation, forming a scaffolded structure ideal for technical training. At the base is remember, such as listing tool parts or naming gases used in deposition. Next is understand, explaining how plasma reacts with process gases during peeled. The third level, apply, involves hands-on tool operation, such as performing recipe edits or aligning wafer cassettes. The fourth, analyze, is vital for troubleshooting, like identifying causes behind temperature non-uniformity. Fifth is evaluate, assessing tool performance metrics and making optimization decisions. Finally, create refers to innovating, designing new chamber processes or custom automation routines. Semiconductor training should align tasks to these stages. For instance, a technician might first recall chamber components, then gradually progress to analyzing cycle time losses or designing yield improvement plans. Using action verbs aligned with each level helps trainers set expectations and measure growth, ensuring trainees move from memorization to high-level problem-solving and innovation. Practical adult learning strategies in fab training. To meet the needs of adult learners, semiconductor training must start with job relevance. Every module should open by explaining how the topic, like pump maintenance or recipe uniformity, directly affects fab goals such as yield, safety, or throughput. Next, clear goals must be defined. Trainees should know specific milestones, such as completing etch simulator drills or passing SPC quizzes. Learning must be interactive. This includes hands-on labs, chamber walkthroughs, or troubleshooting exercises that mimic real fab tasks. Reinforcement is also essential. Use quizzes, supervisor check-ins, and weekly reviews to ensure content sticks. Training should link to real metrics. For example, mastering a cleaning procedure should connect to a measurable drop in particle counts. Lastly, practice must occur under realistic conditions. Use mock alarms, real tools, or shift-based drills to simulate fab pressures. Research from CDC shows adults retain up to 90% of content through active learning, far outperforming lecture-only methods. Connecting theory to real-work outcomes. Training should never feel theoretical or disconnected from fab realities. Every concept must tie directly to results on the floor. When teaching chamber operations, emphasize how precise execution lowers defect density or improves cycle time. Use actual case studies and incident reviews, like a tool miscalibration that led to wafer scrap, to show consequences and reinforce learning. Immediate application is key. If a technician learns chamber cleaning, let them practice that same day to reduce contamination rates. Spaced repetition further deepens retention. Reinforce procedures in morning huddles, shift handovers, or weekly drills. This sustains skills and builds long-term confidence. One powerful example: a fab that implemented regular tool calibration training reduced scrap by 15%. This kind of outcome proves training isn't academic, it's operationally vital. By continuously linking training content to measurable results, learners see purpose, take ownership, and improve their performance from day one. Role-specific applications. Technicians and engineers. Training must reflect the distinct responsibilities of technicians and engineers. For technicians, the focus should be on Bloom's apply and analyze levels. Their key tasks include operating tools, performing maintenance, responding to alarms, and identifying process irregularities. A practical example is simulator-based training, where they load wafers, adjust tool settings, and respond to simulated fault conditions. Engineers and R&D professionals, however, operate at Bloom's evaluate and create levels. They analyze SPC charts, develop new recipes, and design experiments for process improvements. For instance, an engineer might evaluate CFD simulation data to optimize gas flow in an ALD chamber. Regardless of role, all learners benefit from being treated as co-designers in the training process. Allowing them to select modules, suggest improvements, or personalize learning paths fosters self-direction and relevance. Customizing training by role and prior experience makes content more engaging, efficient, and aligned with long-term career goals. Best practices and industry recommendations. Leading training programs in semiconductor manufacturing blend theory with practice. First, balance core knowledge, such as physics, safety protocols, or material science, with direct hands-on skills. Next, use blended learning approaches. Combine simulations, virtual reality labs, and real equipment to make training immersive and engaging. Cognitive progression is critical. Scaffold learning, so trainees move from recalling basic tool components to troubleshooting process deviations. Reinforcement must be ongoing. Use spaced repetition, weekly drills, and refresher certifications to keep skills sharp. Align with industry benchmarks like the Festo training model, which emphasizes job relevance and learner autonomy. Research confirms this works. Programs that apply adult learning principles alongside technical content see 40% higher retention rates and a 35% faster time to proficiency. That means technicians are productive sooner and engineers make better decisions faster. Whether it's VR walkthroughs or peer learning groups, the best programs keep learners engaged, challenged, and progressing toward fab readiness. Key takeaways and conclusion. Effective semiconductor training hinges on combining adult learning principles with structured cognitive growth. New hires, especially those from science and engineering, must be shown why the content matters, what success looks like, and how their skills impact the fab. The best programs do 4 things: explain job relevance, set clear goals, promote active learning, and reinforce key skills consistently. Role-specific paths are essential. Technicians focus on applying and analyzing. Engineers focus on evaluating and creating. Every learner should feel like a collaborator, empowered to shape their development. Feedback loops and flexible learning paths deepen engagement. Most importantly, training must guide learners from foundational knowledge, like understanding deposition chemistry, to advanced tasks like optimizing cycle time or creating new clean protocols. The result is a team of job-ready professionals, technicians who can solve equipment issues in real time, and engineers who innovate to improve fab efficiency. That's the ultimate measure of successful training.